Hello and welcome. To conclude this week's lectures, I thought I would record something very short video to describe all these various types of classifications of operators based on various different properties and ideas, and sort of present them in one way. It's not complete or anything, but still I think hopefully it'll give you it'll be useful for refreshing your memory on what these operators are and how they are all related to each other. Okay, so maybe it's good to see it. Quick recap. So I think this recap will be useful because some of what I'm going to say will sort of throw you back to what we studied a long while ago. We've been looking at vector spaces over scalar field, which is real or complex, and there is this linear map, which is the key object of study for us, and is represented by a matrix. And null and range space are important to understand what the linear map is, and their dimensions add to the overall dimension. That's a very nice result. Then you can use it to solve linear equations, and then there is this 4 fundamental subspaces of the matrix and their connections to the operator, its adjoint and all that. And then eigenvalue and eigenvector played a very crucial role in simplifying the matrix representation, and then telling us more about what the operator is doing. Once inner products came in, we used orthogonality, orthonormal basis, simplified quite a bit of things about operators. In particular, we know that there is a orthonormal basis with respect to which there is an upper triangular matrix for any operator. Okay, and then orthogonal projection is something we studied, adjoint, all the properties that adjoint has, and then we started looking at these various types of operators and special properties that hold for them, particularly self-adjoint, normal, positive, and isometries. We also studied projections a little bit, but these are the 4 main operators in inner product spaces, and they have a lot of connections to each other and very interesting properties and all that. And I'll say a few words from a high level about all these 4 types of operators in this lecture. Okay. So let's look at the first classification or first way of thinking of all these things. So you remember we also had this notion of an invertible operator and diagonalizable operator. So this also is very important, and we haven't maybe talked about it quite a bit, but invertible means the range is the entire space, and then you can go back, right? So that's one way of defining for operators. That's good enough. Diagonalizable is something which we know that there is an eigenvector basis, and it can go to a diagonal representation. But in this slide, I wanted to talk only about null and range space, and what are the various things we know about types of operators and their null space and range space and all that. I wanted to collect all of that together. If you take any operator, we know that the dimension of the null and dimension of the range will add up to n. Okay, and then we also have this nice result connecting the operator and its adjoint. The null of T is range of the adjoint perp, the orthogonal complement. And range of T and range of T star have the same dimension. This is the row column rank result that we know. And then there is an upper triangular matrix with respect to an orthonormal basis for any operator. So these are good properties for any operator. In particular, if the operator is invertible, the range is going to be full dimension, null is 0, right? So that's a nice simple property to have. Diagonalizable, really, null and range, it doesn't limit it in any way, right? So you can have all sorts of null spaces and range spaces, and diagonalizability is possible. Okay, so there's no special property directly that one can talk about for diagonalizability. Okay, now once you have normal, so there is the self-adjoint. If T is T star, then T and T star do the same thing, and but there is this normal operators which commute with this adjoint, not exactly equal, but they commute. So it's almost like similar in some sense, right? So T star is T star T, and you see a lot of things about T and T star become the same once it's normal, right? Null space is the same, range space is the same. In fact, null is the orthogonal complement of the range for the operator, for a normal operator. So these are all nice points to remember. No, these are all just defining properties. It's not like these are properties. Let me repeat myself. These are properties that these types of operators satisfy. Some of them are if and only if, some of them are not, right? So I think you'll be careful about it. You can have null T being range T perp without the operator being normal. All of these things are possible. Okay, so many of these properties, particularly for normal and all, are not if and only if. Okay, But some are infer only. If, like for instance, invertible is that's the defining property, and various other things. So just I thought I should collect all these things together in one place in case you need to use it for something. This is how it works. Okay. Of course, self-adjoint is a subset of normal. Okay, and also something that holds for normal will hold for self-adjoint. And if you think about it, positive operators are also self-adjoint. So all these properties of null space will hold for positive. Isometries are also normal. So whatever properties that whatever holds for normal will also hold for it. So that's why I've just stopped with normal. All the other guys will come in into that. Okay. So this is one type of summary. The other more interesting sort of look is this sort of colorful slide, and I think usually I don't use many colors in the slides, just white and black. But this one I thought there is a genuine need for multiple colors to get the idea through. The classification or understanding in terms of eigenvalues and eigenvectors is what makes the whole thing very interesting for operators. We have this big world of operators. I've drawn like a Venn diagram, rough Venn diagram, to give you an idea of how the containment and all works. You have the world of operators, then within that is invertible operators. In terms of eigenvalues, if you think about it, invertible operators have all non-zero eigenvalues, right? So that's the invertible operators. And then there are these diagonalizable operators. Okay, so now diagonalizable operators, the best way to talk about them is in terms of eigenvectors, right? So there should be an eigenvector basis, a basis for the space full of eigenvectors of the operator. Then that is diagonalizable. Now diagonalizable may be invertible, may be non-invertible. So you see that big partial intersection with invertible, and there is I've drawn it very big because I have to put many more things there, but it's true that diagonalizable is quite big. It's a big set in terms of operators. There are lots of diagonalizable operators out there. Okay, so that's the picture for you. Now inside diagonalizable, we go in and we classify way more. Of course, there is also a lot of operators outside diagonalizable which you might want to classify and all that, but we are not looking at that too much. We are looking at inside diagonalizable. Okay, for now, many of the classifications we looked at. So one big set is this normal operator. So normal operators are very interesting because they are not just diagonalizable, they are diagonalizable with respect to a orthonormal basis. Okay, so that's what I've indicated here. So you see normal becomes subset of the diagonalizable, but normal may be invertible, may not be invertible. Okay, so it will also intersect with invertible, but it may be invertible, may not be invertible. So both are possible for normal. Okay, now inside normal you have these operators called self-adjoint operators. These are definitely normal, but the specialization there is that self-adjoint operators, on top of having an orthonormal eigenvector basis, they're also going to have real eigenvalues. Okay, so that is a defining characterization for self-adjoint. One step more, you have an orthonormal basis, and then you have real eigenvalues. Then you have a self-adjoint operator. Okay, so that's sort of from normal to self-adjoint. The specialization is the eigenvalues are additionally real. Okay, then we studied these positive operators and isometries. So let me come to positive. Positive is quite easy to classify. Positive, just among the self-adjoint operators, positive is those that have non-negative eigenvalues. So you go from orthonormal eigenvector basis you have, and then you specialize on the eigenvalues. Real eigenvalues, you go to self-adjoint. Non-negative eigenvalues, you go to positive. So now, because I've said non-negative, positive eigenvalues, positive operators may be invertible, may not be invertible. If they have zero eigenvalues, then they will not be invertible. So they lie on both sides of the invertible thing. So they'll have only a partial overlap with that. Okay, and then we studied isometries. Now, what are isometries? Isometries are normal, and then they have eigenvalues with absolute value 1. Okay, every eigenvalue has absolute value 1, and isometry also preserves norm, preserves inner product. So it's sort of, it has to be invertible, right? So it's clearly invertible. So isometries will lie entirely inside the invertible set. Okay, so every isometry is invertible. No eigenvalue is 0, right? So all eigenvalues are non-zero. So it's going to be invertible. Now, can isometries be self-adjoint? It's an interesting question. So if an isometry has to be self-adjoint, its eigenvalue should be either +1 or -1, right? So absolute value should be 1. Now self-adjoint means eigenvalues are real. So if you say isometry which is self-adjoint, then almost you're looking at eigenvalues which are +1 or -1, right? So only when it's complex it's a little bit more interesting. There's more range. When it's real, when the eigenvalues are real, it is just +1 or -1. You don't have this e power I theta. It's just +1 -1, right? The theta is not allowed to vary arbitrarily. Okay, so there can be some self-adjoint isometries, but a whole bunch of them you expect to be not self-adjoint. So that's why I put a small overlap with self-adjoint, a slightly large overlap there. Okay, and what about positive? Can you have an isometry which is positive? I think that the only identity is like that, right? So the identity that way is a special operator. I've shown that it's everything, right? Everything is invertible, it's self-adjoint. Of course, it's invertible. It lies on this side of the red thing. It's normal, it's self-adjoint, it's positive, it's isometry, diagonalizable, everything. So identity is sort of there. I think isometry and positive intersect only in identity. Okay, isometry means eigenvalues should be +1 or -1. Positive means eigenvalues are non-negative, so -1 even is eliminated. So all eigenvalues are 1 and you have an orthonormal basis, that is identity, isn't it? So you have identity coming in there, and that's that. Okay, so that's the picture. I don't know if your sense of color agrees with the color or not. I don't know if the words and the type of operators and their colors are compatible according to some code you might have, but it's clear enough. You can see this picture is reasonable. Maybe I could have made it a little bit more symmetric by adjusting the positive and isometry to have the same size, etc. But it's okay. I mean, it comes out quite reasonably. So this picture sort of tells you how eigenvectors, eigenvalues are used to nicely classify these various types of operators and in relation to their adjoint, and then and clearly you can see how the spectral theorem helps us to really understand what is going on here. Okay, so that's a picture for operators and their eigenvalues, eigenvectors. Okay, the last piece of information I wanted to talk about is some things which were not covered so far. A few pieces of information which sort of relate to the norms inner products, but maybe not very obvious or clear in some sense. We saw this nice interesting result that if in a complex space, if you have inner product of TVV, that this quadratic form, if it is real, then it has to be, then the operator has to be self-adjoint both ways, right? So if it's if and only if, so it's a very interesting characterization of self-adjoint. And then we also saw normal if and only if the norm of TV and the norm of T star V are the same. See, remember, the self-adjoint means TV equals T star V, right? So T and T star are exactly the same. So in normal, T and T star need not be the same. T star equals T star T, but their norm has to be the same. Okay, so it's so strong. I mean, it's a normal. A norm is quite a strong constraint on the operator T. And for isometry, we saw that norm before the transform and after the transform have to be equal. But more interestingly, for any two vectors, the inner product has to be preserved by the isometry. So that's an isometry. So these are nice, interesting properties. And we also saw this other very interesting property which helps us prove the spectral theorem and all that, right? So normal means eigenvectors corresponding to two distinct eigenvalues are orthogonal. Okay, so that's at the heart of everything. I didn't quite put it down, but we spoke about the spectral theorem before, so it's sort of hidden in there. Okay, so hopefully these three slides sort of gave you a just a high level view on how this operator classification and all of that worked, and hopefully that concluded the last couple of weeks. This sort of summarizes all that we have seen so far in terms of classifying operators. So going forward in the next week, we will study two types of decompositions of operators. Okay, the first one is called polar decomposition. It is sort of interesting, but maybe not. I mean, maybe it has applications. I have to look at it more closely. But the second one is called the singular value decomposition. Okay, and today, if you rank applications of linear algebra, singular value decomposition will come way up on top. It's used in so many different areas, from communications, compression and learning, and so many other areas. So singular value decomposition gives you a way to understand an operator, understand the large matrix and all the relationships between the entries there, and we will spend some time to understand how the SVD works and why it is so widely popular and it gives a very nice and simple way to understand operators. So at the end of it, when you look at SVD, people sort of disappoint, say you should have taught SVD first, but it takes a little bit of time to work towards that. So I think SVD is a good topic to sort of conclude our lectures in linear algebra. So next week we'll do SVD and something called polar decomposition. Okay, thank you very much.